everyone. My name is Na Liu, a doctoral researcher from Dr. Priya Research Group. Today, I would like to briefly introduce ferroelectric domains. Before introducing what ferroelectric domains are, let's start with what ferroelectrics are. Ferroelectrics are a certain dielectric material that exhibit a spontaneous electrical polarization. And these polarizations exhibit at least two equilibrium states in order to stabilize the material electric polarization. Additionally, those spontaneous polarization are available to be switched by applying an external electric field. This classification of dielectrics can tell us that ferroelectric materials exhibit the property of piezoelectricity, which means that the ferroelectric materials can generate surface charges by applying mechanical pressure, and also vice versa. In addition, ferroelectric material also exhibit the property of ferroelectrics, which means that the spontaneous polarization in the ferroelectric materials is temperature dependent. And this critical temperature where the spontaneous polarization can be generated is so-called Curie temperature. The most important and most unique property in ferroelectric material is the reversibility of its spontaneous polarization under the external electric field. And ultimately, this will generate the fingerprint of the ferroelectrics, which is so-called hysteresis loop. Few examples of ferroelectrics can be given here. There are AbO3 perovskite materials such as boron titanium oxide, lead titanium oxide, or the lead zirconate titanium oxide, which is very famous, can be abbreviated as PZT. And also the polymer-based ferroelectric materials is the PVDF. And in the single crystal family, the lithium niobate is quite famous. Ferroelectric materials have many important applications, such as ferroelectric material can be used as the non-volatile random access memory used in the chips. This application utilizes the switchable polarization states of the ferroelectric materials to store binary data. And these memory devices offer fast read and write speeds, low power consumption, and high endurance compared to the conventional flash memory. In addition, by using the piezoelectricity, ferroelectric materials can be used as piezoelectric sensor to sense the pressure or vibrational force. It can be also used as piezoelectric actuator, which can generate precise and rapid mechanical displacement, which is useful in positional or vibration control. Moreover, ferroelectric materials can be also used in energy harvesting application to convert the mechanical vibrations or temperature fluctuations into the electrical energy. Moreover, by using the ferroelectricity property, the ferroelectric materials can be used as infrared sensor to detect motion or presence. These are commonly used in the security systems or home automation. And the last but not least, ferroelectric materials can be also used in electro-optical devices, such as waveguide, optical switches, optical modulators. This can be used to in the high-speed communication or optical signal processing. In this all these ferroelectric properties are used in different applications. Ferroelectric domain and or the domain wall motion played a very critical role in their properties. So how this domain are formed, how the domain wall are moved. Before introducing that, let's start with the orange of the ferroelectricity. Let's take the ABO3 perovskite structure as an example, since this structure is the most important ferroelectric crystals. As you can see that in the ABO3 system, the A side cation sit on each corner on the unit cell. The oxygen is located on the fifth center position, building an oxygen octahedral within this oxygen octahedral. The central B cation is situated. In the high temperature, this phase is a so-called power-electric phase. The energetically favored position of the B cation is in the center of the unit cell, which means that the center of the negative charge and the center of the positive charge coincide, which leads to a net polarization of 0. So in this cubic phase, there is no ferroelectricity, there is no piezoelectricity, neither the power electricity. So in order to generate such property in the system, we have to decrease the temperature to the so-called Curie temperature, and then induce the phase transformation. Let's take the barium titanate oxide as an example. So by cooling the temperature below the Curie temperature, we first transform the cubic phase to the tetracnol phase, where the B side cation is shifted into an off-center position, creating a permanent dipole moment. This is so-called spontaneous polarization. So in the tetracnol phase, there are 6 possibilities of this spontaneous polarization state. By further cooling it down, the phase will transform to the rhombohedral ferroelectric phase, where there are 8 possible spontaneous polarization orientations. If you consider the orthorhombic phases, there are like 12 possible spontaneous polarizations. And the definition of the ferroelectric domain is those region within which all the dipole moment, that means all the previous mentioned spontaneous polarization, are arranged in the same direction. And this domain size ranges from the several nanometer to several micrometer. And the interface to separate the different domains are so-called domain walls, with the thickness of about like 1 to 10 nanometers. Take the tetracnol phase as an example. Let's introduce how the 180 domain and 90 domains are formed. So in the single domain crystal, the spontaneous polarization developed in the ferroelectric phase is accompanied by an apparent surface charges. This in turn gives rise to a depolarized field within the crystal. And this phenomena is energetically unfavorable. So in order to minimize this electrostatic energy associated with this field, the crystal has to split into regions of the polarization with anti-parallel orientations. So this domain are so-called 180 domains, and the interface are between the anti-parallel domain orientation are so-called 180-degree domain walls. And so when the crystal have a mechanical elastic constraint, So the non-180-degree domain wall will be formed in order to minimize this mechanical elastic energy in the system. So for tetragonal phase, this 180-degree domain are 90-degree domains. In different phases, only distinct angles between domain walls are possible, which are defined by the possible spontaneous polarization axes of the crystal phases. So for each phases in the ferroelectric, the different domain walls are written here. So here are some domain patterns which are characterized by using piezo response force microscope in the different ferroelectric system. So this one presents the domain patterns PFM image in the barium titanium oxide system as its orthorhombic phase. By combining the vertical PFM image and lateral PFM image, the 60-degree, 90-degree, and 180-degree domain walls can be identified. In the PCT-PCT ceramic system, very complex domain pattern can be captured because of many boundaries exist in the ceramic, give very complex electrostatic and electromechanical field. In the multiferroic ferroelectric single crystal, classical vortex domain walls can be visualized by using piezo response force microscope. As I mentioned that domain wall motion play a very important role on the ferroelectric property in the different applications. So in order to control this domain wall motion to further modify the functionality of the ferroelectric materials, many ways can control that. The first way is by applying the external electric field to induce the domain switching and further control the domain wall motion. And ultimately, we will generate a hysteresis loop, which is also called P loop in the ferroelectrics. So initially, the domain spontaneous polarization are randomly distributed. And so the net polarization are 0. By applying small AC field, limited translation of the domain walls is seen, and polarization increases linearly with the field. By further increase the electric field, polarization increases rapidly due to the irreversible switching and the domain wall motion until it reaches to a saturation situation where the domain are aligned with respect to the external electric field. By decreasing the electric field to 0, due to the domain, subdomain cannot reverse to the original state on time. So the remnant domain can be induced, which is called remnant state. By further decrease the electric field to the negative EC value, all the domain come to all the net polarization reach to 0. And where the domain begins to align conversely with respect to the negative field. And by further decrease the negative electric field, the negative polarization and the reverse alignment of the domain occurs until it reaches to the ultimate and or saturated situation. So in the polarization reversal process in ferroelectrics, there are 4 steps which need to be discussed here. So initially, the domain needs to be nucleated in the reversal direction. By increasing the electric field, the forward growth of this nuclei will be processed. By further increasing the electric field, the sideways growth of the domain will be presented, followed by the collineages of the preferred domain, and ultimately a reversal process can be formed. Another way to control the domain wall motion is by changing the temperature. So for instance, in this BTO system, by increasing the temperature, the phase can transform to also rhombic phase to tetrachonal phase. So they use the piezo response force microscopy to capture how the domain wall move or how the phase transport and with respect to the domain wall, the domain rearranging in the different phases. So I will then end this talk by using the concluded method to control the domain wall motion. So here are the conclusive way to monitor the domain wall motion. One way is material doping, or we can also do compositional engineering. Also, we can apply the mechanical stress or external electric field. We can also monitor the temperature to the ferroelectric material. Additionally, some nanostructuring on the ferroelectric can be done to control the domain wall motion, such as the thin film or nanowire configuration of the material. The last but not least is the interface engineering. So by designing the heterogeneous structure in the ferroelectric or making a multi-layer ferroelectric material, the domain wall motion can be also controlled in order to modify the functionality of the ferroelectric materials. So thank you for your attention.